Module 1, Lecture C, Arrays and Tables. By the end of this lecture, you will be able to create NumPy arrays for numerical engineering calculations and image-like grids, use Pandas DataFrames to inspect, filter, and summarize tabular mechanical datasets, and build basic Matplotlib plots that reveal trends, outliers, and relationships in engineering data. NumPy Array Basics. Array Creation. Creating arrays is a key first step in NumPy because it organizes numerical data for efficient storage and fast computation. NumPy arrays hold values of the same type in a structured layout, making them well-suited for data such as temperatures or sensor readings. The shape of the data matters. A row is one-dimensional, a grid is two-dimensional, and stacked grids create higher dimensions, which affects later calculations and visualizations. In engineering, arrays organize measured data or generate pattern data for analysis and simulation. They can support tasks like cleaning, scaling, plotting, or modeling values across a physical system. Arrays filled with zeros or constants also provide useful starting points, such as an empty image or a uniform initial temperature. This structure makes engineering calculations more efficient and easier to manage. When creating arrays, choose their shape, dimensionality, and data type carefully. These choices define how the data is organized, what kind of structure it represents, and how precisely values are stored. Good array design supports accurate calculations and meaningful engineering models. Python code, array creation. Create arrays to represent engineering measurements, then check their shapes, dimensions, and data types to understand their structure. You can also visualize a temperature grid as an image-like array to see patterns across the data. We begin by importing NumPy for efficient array handling and numerical operations, along with Matplotlib's plotting tools for creating visualizations. Together, these libraries provide the basic tools needed to create, manipulate, and display data arrays. Two one-dimensional NumPy arrays are created to store related measurements, one for beam positions in centimeters, from 0 to 100, and one for the matching temperatures in degrees Celsius. Together, they pair each position with its temperature for later analysis or visualization. We use NumPy to model 7 evenly spaced positions along a 12-foot pipe. Then we create a matching pressure array where every position starts at 55 psi, giving the pipe a uniform initial pressure. A 4x5 floating point grid is initialized with zeros, then a small central section is changed to 85. This creates a higher value block in the second and third rows and the third and fourth columns, representing a thermal hotspot. We first confirm that the beam position data and temperature data have matching shapes, so every position has a temperature value. Then we check that the thermal grid is 4x5, ensuring it is correctly structured for later use. This section checks key properties of several data arrays. It reviews the size of the beam positions, the data type of the temperature values, and a small sample of the pipe pressure data. It also confirms the thermal grid dimensions and reports its maximum value to show the highest temperature represented. A new plot is created to display the thermal grid as an image. The grid uses a hot color map, so warmer colors represent higher temperatures, with the origin placed at the bottom left. A color bar labeled in degrees Celsius, a title, and axis labels help explain the visualization. The layout is adjusted for neat spacing, and the plot is then shown on the screen. This script uses NumPy to create engineering measurement arrays and Matplotlib to visualize them. It defines matching position and temperature data, creates pipe positions with constant pressure values, and builds a two-dimensional thermal grid with a hotter region to represent a heat map. It checks array shapes, reports key summaries such as the maximum temperature, and displays the grid with labeled axes, a color scale, and a hot color map to show the temperature distribution clearly. Array creation. Creating arrays in NumPy is a key first step because it shapes how data is stored and used in calculations. NumPy arrays hold same type values efficiently, making large engineering datasets faster to process. One-dimensional arrays can represent measurements like strain, while two-dimensional arrays can represent values across a surface, connecting real-world data to Python computation. Arrays can be built from existing data, such as sensor readings or load values, so the data can be analyzed together. Engineers also create arrays for simulations, such as defining time points, positions, or grids. When the structure is known before the values are, arrays often begin with placeholders like zeros or ones and are filled as the simulation runs. When working with image-like grids, an array's shape is essential because it preserves the meaning and relationships of the data. Grayscale images, thermal maps, surface heights, and stress fields all rely on correctly arranged values to reveal patterns such as hotspots or deformation zones. Understanding how to create arrays with the right dimensions is a foundation for reshaping data, applying mathematical operations, and connecting analysis to real-world systems. Python code. Array creation. Create arrays to support engineering calculations and understand the difference between one-dimensional data and grid-based data. Keep results compact and easy to read so the output stays clear and useful. The script begins by importing NumPy for efficient numerical work with arrays and mathematical operations. It also imports Matplotlib's plotting tools to create visualizations. Together, these libraries provide the foundation for the data processing and plotting that follow. A NumPy array is used to store 5 strain readings measured in microstrain: 120, 135, 128, 142, and 150. Keeping these measurements in an array makes them easy to manage and analyze later. The NumPy linspace function creates 5 evenly spaced beam positions from 0 to 1 meter. This provides consistent intervals along the beam, which is useful for simulations or calculations over a physical length. We initialize a deflection array in millimeters using NumPy's zeros-like function. It creates zeros with the same shape as the positions array, making the two arrays compatible for later calculations. A small thermal image can be represented with NumPy as a two-dimensional grid of temperature values. In this example, the grid has 3 rows and 3 columns, with each value showing a temperature in degrees Celsius. This simple array helps model how temperature varies across a small area. We first confirm that the strain measurements and beam positions have matching shapes, so each measurement aligns with a position. We also check that the thermal image grid is 3 by 3, ensuring it is correctly structured for analysis or visualization. The output checks the shapes of the strain data, beam positions, deflection placeholder, and thermal grid to confirm that each array has the expected structure. It also verifies that the deflection data aligns with the position data for consistent calculations. Finally, it reports the highest temperature in the thermal grid as a quick summary of the recorded temperature range. This plot displays a small thermal grid as an image using a warm color map, where hotter values appear in warmer colors. The grid is oriented with the origin at the lower left, and a color bar labeled in degrees Celsius explains the temperature scale. A title and axis labels identify the grid and its row and column positions, while the layout is adjusted so the final figure appears neatly. This script shows how to use NumPy and Matplotlib to create and inspect arrays for engineering data. It defines one-dimensional arrays for strain readings, beam positions, and deflection values, along with a two-dimensional temperature grid. The code checks array shapes, reports the maximum temperature, and displays the grid as a heat map with a color bar to show how temperature varies across the area. Array properties. A NumPy array is a structured object, not just a container for numbers. Its shape describes the size of each dimension, and the number of dimensions tells whether it behaves like a simple list, a matrix, or a more complex grid. These properties matter because they determine how calculations are applied, and shape mismatches can cause errors or misleading results. A NumPy array's data type determines what kind of values it stores and how much memory each value uses. Choosing the right type, such as integers, decimals, or booleans, affects precision, performance, and storage efficiency. Checking the data type helps ensure the array is suitable for the calculation and avoids problems like lost detail or unnecessary memory use. Understanding NumPy array properties helps you manage large numerical data efficiently. Checking an array's size, memory use, and dimensions shows how much data it contains and whether its structure matches the intended meaning, such as rows, columns, layers, or time steps. This reduces errors and supports more reliable numerical analysis in engineering work. Python code. Array properties. Explore key NumPy array properties used with engineering data, including shape, number of dimensions, data type, and memory use. Keep the arrays small so the results stay easy to read and interpret. The code starts by importing NumPy, a Python library used for efficient numerical computing. This gives the script tools for working with arrays and performing the mathematical operations needed later. We create a one-dimensional NumPy array to store 4 temperature readings in Celsius. This sensor vector uses floating point values, making it efficient for numerical processing and later operations. A two-dimensional NumPy array is used to store pressure values in kilopascals as a grid with 2 rows and 3 columns. This structured format makes it easier to work with and analyze pressure data, especially when studying spatial pressure distribution in engineering applications. We use NumPy to create a two-dimensional grid that represents a grayscale image. Each value is a pixel intensity, from 0 for black to 255 for white. The data is stored as unsigned 8-bit integers, the standard efficient format for 1-byte image pixels. We organize each array by pairing it with a clear descriptive label, so its role in the engineering context is easy to track. These label and array pairs are stored together, making it simple to loop through them later and produce clearly identified output. The code goes through each labeled array and prints a brief summary of its key properties. It reports the array's label, shape, number of dimensions, and element data type, giving a quick view of how the data is structured and stored. The code goes through each labeled array and reports 2 key details: how many elements it contains and how many bytes of memory it uses. This gives a quick view of each array's data size and memory footprint, which helps assess resource use in engineering applications. Define the expected pressure grid shape as 2 rows by 3 columns. Then use it to check the actual grid shape. This validation helps ensure the data structure matches the intended design and prevents errors in later calculations or analysis. The pressure grid's shape is compared with the expected dimensions to confirm it has the right structure. The result is a true or false value that indicates whether the grid matches what was anticipated. We use NumPy's mean method to find the average pressure across the entire grid. This gives one representative pressure value, which helps summarize the grid for engineering calculations or comparisons. The code first checks that the pressure grid has the expected shape, confirming the data is structured correctly. It then uses NumPy to calculate the grid's average pressure and prints the result rounded to 2 decimal places. This script demonstrates how to inspect key properties of NumPy arrays, including shape, number of dimensions, data type, element count, and memory use. It uses simple one-dimensional and two-dimensional examples, then checks whether a pressure grid has the expected 2x3 shape. It also computes the grid's mean pressure, showing how array inspection supports basic engineering calculations. Pandas tables, data frame basics. A Pandas data frame is a structured table in Python, similar to a spreadsheet, with rows for records and columns for variables. It is useful for real-world engineering data because it can keep numerical, categorical, and time-related information together. By keeping each row aligned as a complete record, a data frame helps analysts view and work with the whole dataset consistently. In a data frame, column and row labels help keep data clear and meaningful. Column labels name the variables, while row labels identify each record, such as by number, timestamp, or part number. Together, they preserve context so measurements in mechanical datasets can be interpreted and manipulated correctly. Before analyzing a data frame, first inspect its structure and data quality. Check the column names, size, sample records, data types, and any missing or unexpected values. This helps prevent errors such as failed calculations from text stored as numbers or gaps in temperature data. Treating the data frame as both a computing object and a record of physical measurements supports reliable mechanical data analysis. Python code, data frame basics. Data frames store engineering measurements in labeled tables, making the data easier to inspect before analysis. Using small examples helps keep the output clear, readable, and focused. We begin by importing Pandas and NumPy to prepare for data analysis. Pandas helps organize and analyze structured data in tables, while NumPy supports efficient numerical calculations with arrays and mathematical functions. We create a small dataset to represent mechanical test results, using a dictionary where each entry will become a column in a data frame. It includes specimen identifiers and the material type for each sample, such as steel or aluminum. This structure makes it easy to turn the data into a table for later analysis. The code creates a dictionary that organizes measurement data for analysis. It includes load values in kilonewtons, deflection values in millimeters, and temperature readings in degrees Celsius, with one missing load value marked as not a number. This structure makes the data easy to convert into a data frame for further work. A Pandas data frame is created from a dictionary of mechanical test specimen data. The dictionary defines labeled columns for details, such as specimen identifiers, materials, and measurements. This organizes the data into a table, making it easier to work with and analyze later. The specimen identifiers are used as the data frame's row labels. so each row can be referenced by its unique specimen ID. This makes the data clearer and easier to work with when selecting or manipulating specific rows. Begin by inspecting the data frame to confirm it is organized correctly. Check its size, column names, row labels, and each column's data type to understand what data is available and whether it is numerical, categorical, or another kind. This quick review helps verify the dataset before starting analysis. Use the Pandas head method to quickly preview the start of a data frame. Showing the first 3 rows gives a concise view of the data structure and contents, which is especially helpful for large datasets. A print statement can label the output as the first rows and display those top records clearly. To find missing values in a data frame, use the isName method to identify them, then sum the results for each column. Converting the counts to a dictionary makes it easy to see which columns have missing data and how many values are missing. The data is summarized by focusing on load in kilonewtons and deflection in millimeters. A Pandas summary method provides key statistics, including the mean and maximum values. From this summary, the mean load and maximum deflection are extracted, rounded to 2 decimal places, and printed to give a concise view of the dataset's main numerical features. Filter the data to keep only specimens with deflection greater than 2.5 millimeters. Then collect the index labels from those rows as a list, and print it to show which specimens have high deflection values. This script shows basic Pandas data frame operations using mechanical test data. It creates a table of specimens with material, load, deflection, and temperature values, then checks the table's size, labels, data types, and first records. It also identifies one missing load value, calculates key summaries such as average load and maximum deflection, and filters the data to find specimens with deflection greater than 2.5 millimeters. Filtering data frames. Filtering a data frame means selecting only the rows or columns needed for a specific analysis. In engineering data, this helps narrow large datasets to relevant conditions, such as certain materials, machines, or measurement ranges. By focusing on the right subset, engineers can examine the data more carefully and make better decisions. Filtering tabular data means applying conditions to selected columns so you see only the records that matter. In engineering, this might isolate fatigue tests above a cycle limit, bearings with high vibration, or parts outside tolerance. Combining conditions, such as component type and operating state, creates a focused view that supports more accurate interpretation. Filtering data is an analytical decision, not just a technical step. Before filtering, understand the units, column meanings, and how the data was collected, so you do not remove or misread important information. Missing values, for example, may reveal equipment problems rather than simple errors. Good filtering combines Pandas skills with engineering judgment to focus the dataset, reveal trends, and prepare it for analysis. Python code, filtering data frames. Filtering tables helps engineers focus on the most relevant data. By keeping datasets small and selecting only meaningful rows, the results stay easier to read and analyze. We begin by importing Pandas, a library used to work with tabular data. This gives us access to data frames and other tools for organizing, analyzing, and manipulating data efficiently in the rest of the code. We create a mechanical inspection dataset as a dictionary, where each part has a unique identifier and a corresponding material. The part identifiers label each item, while the material entries, such as aluminum, steel, and titanium, categorize the parts for later filtering and analysis. The code organizes mechanical inspection data by recording each part's diameter, applied load, and test temperature. These measurements are stored together in a dictionary, so they can be converted into a data frame for structured analysis. The data dictionary is converted into a Pandas data frame, turning raw data into a structured table. This makes the dataset easier to manage, filter, and analyze efficiently. We define key engineering limits to filter the dataset. Acceptable part diameters range from 0.998 to 1.008, and high-temperature tests are identified at 75 degrees Celsius. These thresholds help isolate parts outside the desired ranges for focused analysis. We filter the data frame to find parts whose diameter falls below the lower limit or above the upper limit. The matching rows are stored separately so we can quickly identify parts that do not meet the diameter specifications. The data frame is filtered to keep only rows for aluminum parts tested above the hot temperature limit. A row is included only when both the material is aluminum and the temperature is higher than that limit. The result is a smaller dataset containing just those high-temperature aluminum parts. The summary reports how many parts were inspected, how many were out of tolerance, and how many aluminum parts were tested at high temperatures. It also extracts the part IDs for the out-of-tolerance parts and the hot aluminum parts. Together, these counts and ID lists make it easier to identify the key filtered groups and focus on the parts that need attention. The filtered data shows only the key details for aluminum parts tested at high temperatures: the part ID, diameter in inches, and temperature in Celsius. Converting the selected columns to a printable string and hiding the row index creates a cleaner output, focused on the relevant information. This script uses Pandas to review a mechanical inspection dataset and highlight key engineering concerns. It filters parts with diameters outside the allowed range of 0.998 to 1.008 inches, and also finds aluminum parts tested above 75 degrees Celsius. It then reports the total inspected parts, counts for each filtered group, and the relevant part IDs, helping engineers focus quickly on parts that may need closer analysis. Summarizing data frames. Summarizing a data frame means reducing a large table to key statistics that reveal the main patterns in the data. In engineering datasets, measures like averages and standard deviations can answer practical questions about typical values, such as yield strength or torque. These summaries are an important first step before plotting or modeling, because they can also expose missing data or possible errors, such as an impossible negative pressure value. Pandas can summarize data by groups, not just across an entire table. By grouping a data frame using a category such as machine type, test location, material, or shift, engineers can compare results under different conditions. These grouped summaries reveal patterns, such as differences in average hardness or defect rates, that overall averages may hide, and can support better engineering decisions. Data summaries are useful, but they can hide important details, such as outliers, skewed patterns, or large variation. The same average can describe very different datasets, so check spread, missing values, unusual maximums, and whether the sample size is large enough to trust. Good summarizing is an iterative process of reviewing key columns and groups, refining questions, and using the results to draw stronger conclusions from raw data. Python code. Summarizing data frames. Summaries help turn tables into useful engineering insight. Grouping those summaries makes it easier to compare important operating conditions, while keeping tables small helps beginner examples stay clear and readable. We begin by importing Pandas, a library used to work with tabular data. In this script, Pandas helps create a data frame from a dictionary, then aggregate and summarize the data to reveal useful insights. We create a small mechanical inspection dataset using a dictionary, where each entry represents a future data frame column. One column stores unique part identifiers from 101 to 106. This structure makes it easy to convert the data into a data frame for later analysis. The dataset records key inspection and testing information for several parts. It includes the production line for each part, the measured diameter in millimeters, and the load applied in kilonewtons. These values will be organized into a data frame for further analysis. The data includes a set of true or false values showing whether each part passed inspection. These results support later quality analysis, such as measuring pass rates and spotting inspection trends. The data dictionary is converted into a Pandas data frame, organizing it into a table. This makes the data easier to summarize, analyze, and manipulate in later steps. Before summarizing the data, the code checks that the data frame has the expected shape, 6 rows and 5 columns. This assertion acts as a safeguard, stopping the analysis if the data structure is not correct. We summarize the key numeric columns, diameter in millimeters, and load in kilonewtons, using an aggregate function. It reports the count, average, minimum, maximum, and standard deviation, giving a quick view of the data's range and variability. Group the data by production line, then summarize key metrics for each line. Calculate the average part diameter, the highest recorded load, and the average inspection result, which represents the pass rate. This gives a compact view of performance and quality across the different production lines. The code displays an overall summary of the data frame's numeric columns. It reports key statistics such as count, mean, minimum, maximum, and standard deviation, with values rounded to 2 decimal places for easier reading. We introduce a grouped summary by production line, then show the rounded results for easier reading. The summary compares average diameter, maximum load, and pass rate across lines, helping engineers quickly spot performance differences. To find possible outliers, filter the data to keep only rows where the diameter is greater than 25.2 millimeters. These entries may represent parts that fall outside expected measurements, making them important for quality control and further analysis. The output focuses on parts with diameter values above 25.2 millimeters, helping identify possible outliers. It displays only the essential fields: part ID, production line, and diameter. The data is formatted without row indices, so the results are cleaner and easier to read. This script uses Pandas to summarize mechanical inspection data. It builds a data frame, checks its size, and reports key statistics for diameter and load, such as averages, ranges, and variation. It also compares results by production line, including average diameter, maximum load, and pass rate. Finally, it flags parts with diameters above 25.2 millimeters so they can be reviewed as possible outliers. Engineering data plots. Trend visualization. Trend visualization helps engineers turn measurements into clear patterns over time or distance. By plotting data, they can quickly judge whether a system is stable, improving, or degrading. Trends in temperature, vibration, or pressure can reveal risks such as overheating, component wear, or losses in a pipeline. guiding engineers toward likely causes and effects. A trend plot should place variables on the axes in a way that matches their physical meaning. The horizontal axis usually shows an ordered quantity, such as time or position, while the vertical axis shows the measured response, such as temperature or efficiency. This makes patterns easier to see, like how strain changes with load or how temperature changes during cooling, without relying on raw data tables. Trend plots help engineers interpret data by showing patterns that tables can hide, such as outliers, noise, shifts, drifts, and oscillations. By comparing a suspicious value with nearby data, engineers can judge whether it is likely a sensor error, a real event, or a change in system behavior. These visual trends support decisions about maintenance, design improvements, and further data collection. Python code, trend visualization. Trend plots help reveal engineering behavior, while small datasets make examples easier to understand. Clear labels connect each plot to the underlying physics. We import 3 core Python libraries for data work: NumPy for efficient numerical operations with arrays, Pandas for managing and analyzing tabular data, and Matplotlib's plotting tools for creating visualizations. Together, they provide a strong foundation for data analysis and visualization. To make synthetic test data reproducible, the random seed is set to 7, so the same random values are generated each time. A time sequence is then created from 0 to 30 minutes in steps of 2. The base temperature is modeled as a simple linear increase, starting at 24 degrees Celsius and rising by 0.9 degrees for each minute. Random sensor noise is added to the base temperature to make the readings more realistic, using normally distributed noise with an average of 0 and a standard deviation of 0.8. The power is then modeled as a simple linear increase over time, starting at 4.8 kilowatts and rising by 0.04 kilowatts each minute. We use Pandas to create a data frame that organizes the measurement data into one structured table. It stores time in minutes, motor temperature in degrees Celsius, and power in kilowatts, making the dataset easier to analyze and work with. Check the data frame's shape to find its number of rows and columns. Then use an assertion to confirm it has more than 3 rows and exactly 3 columns, ensuring the data has the expected structure before further analysis or visualization. To summarize the motor temperature trend, take the starting temperature from the first recorded value and the ending temperature from the last recorded value. Subtract the start from the end to find how much the motor temperature increased during the test. The code summarizes the motor temperature data by first reporting how many time samples were recorded. It then calculates and prints the total temperature increase from the start to the end of the test. Finally, it states the main trend: the motor temperature rises over time. Create a clear plot of motor temperature over time by setting an appropriate figure size, then drawing a line with circular markers for each data point. Label the horizontal axis as time during the test in minutes, and the vertical axis as motor temperature in degrees Celsius, so the chart is easy to interpret. The plot is finalized by adding a clear title for the motor temperature trend, turning on a subtle grid to make the data easier to read, and adjusting the layout so all elements fit neatly. The completed graph is then displayed for visual interpretation of how motor temperature changes over time. This script creates synthetic data for a motor temperature test over time. It generates time, temperature, and power measurements, adds random noise to imitate sensor variation, and stores the results in a data table. It then checks that the data has the expected size, calculates the overall temperature rise, and reports the sample count. Finally, it plots motor temperature over time, showing a gradual increase during the test. Trend visualization. Trend visualization helps engineers turn measurements into clear evidence of how a system is changing. In mechanical and manufacturing analysis, line plots are useful because they connect data points over time or changing conditions, making increases, decreases, and unusual behavior easier to see. By tracking values such as temperature or stress, engineers can diagnose patterns that may be hidden in raw data tables. A good trend plot makes changes in data easy to see without misleading the viewer. The horizontal axis usually shows sequence, such as time or test number, and the vertical axis shows the measured response. Clear labels, units, and an appropriate scale are essential because poor scaling can hide important changes or exaggerate normal variation. Effective trend visualization combines technical accuracy with sound visual judgment. Trend plots help engineers compare how systems behave across different conditions or trials by showing multiple data lines together. They make it easier to spot patterns, confirm whether a design or process is performing as expected, and detect problems such as drift, instability, or unusual spikes. In this way, trend plots turn raw data into practical decisions about reliability, safety, and design improvement. Python code, trend visualization. Trend plots help reveal important engineering behavior, especially when examples use small datasets that are easy to understand. Clear labels make the results easier to interpret and support better engineering decisions. We import 3 core Python libraries for data work: NumPy for efficient numerical operations and arrays, Pandas for managing and analyzing data with DataFrames, and Matplotlib's plotting tools for creating visualizations. Together, they provide the foundation for data manipulation and visualization. We create time measurements from 0 to 8 hours in 1-hour steps, then pair each time point with temperature readings in Celsius and vibration readings in millimeters per second. Together, these arrays provide the data needed to examine how temperature and vibration change over time. We use Pandas to create a data frame that organizes the data into a structured table. It combines the time, temperature, and vibration velocity arrays into 3 columns, making the dataset easier to analyze and work with. Check the data table's shape by counting its rows and columns. The row count gives the number of recorded time measurements, while the column count shows how many measurement types are included. An assertion then confirms the table has 9 rows and 3 columns, helping ensure the data is complete and correctly structured before further analysis. To summarize the data, calculate the overall temperature increase by comparing the final and initial temperatures. Then, identify the highest vibration value and the time when it occurs. Together, these measures show both the temperature change and the moment of the most significant vibration event. The code gives a quick overview of the dataset by reporting its size, the total temperature change over time, and the highest vibration reading. It also identifies the hour when that peak vibration occurred, which may point to an important event or anomaly. Create a Matplotlib figure to show temperature trends over time, using a line plot of operating hours against bearing temperature. Add circular markers and a red line to make the data points clear. Label the horizontal axis as operating time in hours and the vertical axis as bearing temperature in degrees Celsius, matching the vertical label color to the line for easy identification. Add a second y-axis that shares the same time axis, so vibration velocity can be plotted alongside temperature. Plot the vibration data in blue with square markers. Then label the new axis as vibration velocity in millimeters per second, and color it blue to match the line. The code highlights a vibration anomaly by marking the peak vibration point with a black dot on the graph. It also adds a nearby label calling it a possible anomaly, with an arrow pointing to the marker. This makes the unusual data point easy to identify quickly. The code finalizes the plot by adding a clear title, turning on a subtle grid for readability, and adjusting the layout so elements do not overlap. It then displays the completed visualization, making the machine trend data ready for analysis. This script summarizes machine operation trends by generating time-based temperature and vibration data, storing it in a data table, and checking that the data has the expected size. It reports the total temperature increase, the highest vibration value, and when that peak occurs. It then plots temperature and vibration over time on separate axes, marking the peak vibration as a possible anomaly. The result is a clear view of how the machine's temperature and vibration change during operation. Relationship plots. Relationship plots show how engineering variables change together when tables are hard to interpret. In Matplotlib, scatter plots place each observation as a point, making trends easier to see. For example, tensile strength plotted against carbon content may show a direct trend, an inverse trend, or a scattered pattern that suggests weak relationships or noisy data. Relationship plots reveal patterns in engineering data, such as clusters, outliers, and different operating conditions. For example, pressure, flow, temperature, or strain data may group by system settings, while unusual points can signal sensor errors, unexpected test changes, or possible equipment problems. By making these patterns visible, relationship plots help guide deeper investigation and further analysis. Effective relationship plots depend on clear choices about axes, scale, and category distinctions. The horizontal axis usually shows the input or controlled variable, while the vertical axis shows the response. Colors or markers can separate groups, making it easier to compare patterns across categories. Clear titles, labels, and scales help the plot support accurate interpretation and discussion of real data. Python code. Relationship plots. Relationship plots help reveal patterns between engineering variables. Scatter plots compare paired measurements, and color can distinguish different operating conditions. We begin by importing the main Python libraries needed for data work. NumPy supports efficient numerical calculations. Pandas helps organize and analyze data in DataFrames. And Matplotlib's plotting tools create visualizations. Together, these imports prepare the script for data handling and visualization. We create synthetic pump test data by using a fixed random seed for reproducibility, then defining flow rates from 20 to 102 gallons per minute. Each flow rate is paired with a low, medium, or high valve setting to represent different pump operating conditions. The pressure drop is modeled from the flow rate by squaring the gallons per minute value and multiplying by 0.018. A valve setting adjustment is then added, 18 for high, 8 for medium, and none for other settings. Finally, random noise from a zero-centered normal distribution with a standard deviation of 3 is added to simulate real measurement variation. The pressure is calculated by combining the base pressure, valve setting offset, and random noise to mimic realistic measurements. The data is then organized in a Pandas data frame with flow rate, pressure, and valve setting, keeping all 12 measurements aligned. An assertion checks that the data frame has the expected size, and structure. We start by checking the dataset's size using its number of rows and columns. Then we review the minimum and maximum flow rates in gallons per minute to understand the range of values. Finally, we calculate the average pressure in PSI, rounded to 1 decimal place, to summarize the typical pressure in the data. Set up a new Matplotlib plot with a figure and axis. Then define colors and marker shapes to distinguish valve settings. Low, medium, and high settings are shown with different colors and symbols, making the plotted data points easier to tell apart. The code groups the pump data by valve setting and plots flow rate against pressure drop for each group. Each valve setting is shown with its own color and marker style, with larger markers for visibility. This makes it easier to compare how flow rate and pressure drop relate under different valve conditions. The plot is titled to show it compares flow rate and pressure drop for a pump. The x-axis is labeled in gallons per minute, and the y-axis is labeled in PSI. A light grid is added to make the plot easier to read without distracting from the data. The plot is finalized by adding a legend that identifies each valve setting by its color and marker. The layout is then adjusted so the plot elements fit neatly, and the plot is displayed for visual comparison of flow rate and pressure drop across the valve settings. This script creates synthetic pump test data showing how pressure drop changes with flow rate under low, medium, and high valve settings. It uses fixed flow rates, a quadratic pressure relationship, valve adjustments, and random noise, then organizes the results in a data table and prints a brief summary. Finally, it plots flow rate against pressure drop with distinct markers and colors for each valve setting. In this lecture, you learn to create NumPy arrays for numerical engineering calculations and image-like grids. Use Pandas DataFrames to inspect, filter, and summarize tabular mechanical datasets. And build basic Matplotlib plots that reveal trends, outliers, and relationships in engineering data. In the next module, Module 2, we will go over engineering data workflow. Thank you for your attention. See you all in the next lecture.